All right, next up on our agenda, we have Daniel Hellstrom of Cobham Advanced Engineering Solutions presenting on NOEL-V, a fault-tolerant RISC-V processor IP and recent software releases. CAES is a longtime sponsor of the Flight Software Workshop, and we thank them again for their support this year. Daniel, it is all yours, although I see your webcam on, but I'm not sure. There you are. Yep.
Thank you very much for having us on again. And I'm going to present about the NOEL-V. That's a new fault-tolerant processor IP from us, which is RISC-V compliant. I recorded a Leon-V presentation earlier on, which is available online, and that also could be interesting in this context because I have some slides there which sort of makes a bit of comparison between the NOEL-V and the Leon-V. But this presentation will mostly focus on NOEL-V, and then I will also present a bit about the recent software releases. After all this, it's the Flight Software Workshop. So, when it comes to NOEL-V, I will focus a bit on the improvements that we've made last year on the hypervisor mode, especially. So my name is Daniel Hellstrom. I'm from Cobham at the site in Gothenburg, Sweden, Geisler site. We see ourselves as a world leader in embedded computer systems for harsh environments. We are experts on fault-tolerant computing, and we do mostly processor products, but we also design non-CPU chips, and IPs, which are soft, such as the Spaceway router. That's another non-CPU product. But the commonality is that they target the space applications, even though some, of course, are also applicable on commercial side. Our IPs are available in standard products, such as our components, but they can also be used in FPGAs. So we do provide pre-configured FPGA solutions, but we also help out our customers when they buy IP from us, where they make their own FPGA designs using various technologies, FPGA technologies, and also when customers license to do full custom ASICs. So we provide help and support and certain design services for those customers that want that. Our processors, which are the main products, are based on open standards. So we have the Leon, which has a long flight heritage, and a long heritage, but it's based on a Spark V8 compatible machine. And the NOEL-V, which I'm going to present today, it's compatible with another open standard, RISC-V, that has a momentum at the moment. Our processor is both 32 and 64-bit. Both are designed specific to include fault-tolerant elements to avoid effects of faults from radiation, which is quite common in space environments. But it's not, next slide, please. It's not all about fault tolerance and radiation. It's also other aspects that we need to cover for this environment, such as vibration and shock and vacuum and temperature. And that means that we need to take account for the whole chain, both at design level and testing. So that means that we need to consider which component packages we select, or bonding, or and the silicon technology that we select, and cell libraries, etc. And also our test flows need to be different from commercial, of course, and the generation of evidence and testing from that. So to reach, for example, QMLV classification of components. Next, please. When it comes to radiation, radiation tolerances, there are different kinds of faults that we encounter. So some errors might be permanent faults, which bits, for example, could be stuck at certain values or having other long-term effects. And that is one type of faults, but there can also be transient effects caused by different single event upsets or transients that could cause registers or memory cells to toggle, but once they are reset, those memories are fully functional as before. So that's another kind of protection we need for these kind of errors. And also we can have errors in combinatorial logic in transistor paths, which we need to protect from. Next slide, please. There are different technologies where we put our IPs onto. For example, ASICs, where our components, when we design our components, we select cell libraries which are hardened, and we also use screening to screen away faulty components. But it's important that the cell library has built-in support for protecting against radiation effects and to avoid multi-bit upsets to happen at which we cannot deal with. So and we also need to avoid certain sensitive macros as PLLs, for example, which can be sensitive. So we need to select technologies where PLLs having certain properties can be provided. And when it comes to FPGA, it's similar, but in a different way. So we want to use the fabrics available on the FPGA, which are able to protect from these events. And we use triplication in our FPGA designs by relying on the EDA tools, generating that automatically in some cases. But we need to, the message is that we need to take care of all these different things. If we miss out on one of them, then it's no real point. So that means that we need to understand all the parts of the flow of the design and also use cases where this can be used. Next slide, please. So if there's a little flip somewhere, a change in one bit, that could of course be let's say a one value that changes, and that could be rounded away in software, for example, or be within the valid range and go undetected. That could also be critical, of course. Next, please. But if that bit flip happens somewhere else, it could be a completely different significance. Next, please. So the NOEL-V processor is a fault-tolerant processor. You can turn off the fault tolerance for commercial also. It's compatible with the RISC-V standard. It can both be 64 and 32 bits. And you select on when you instantiate the IP. There are also other major configuration options, which in the RISC-V standard they call extensions. And there you can select different extensions, and then you need to specify those extensions to the compiler. And then the whole tool chain will adapt, both assembly steps and compiler steps. But of course, if there's assembly in the operating system, of course, that needs to be compatible. But otherwise, that is taken care of in the compilers. So you have to just make sure that you have a matching configuration. On the MMU side, we support both 32-bit and 39-bit address spaces. And we have a physical memory protection, PMP, which protects the machine mode. It's more a simpler way of protecting, more like a bit mask of addresses, masking out certain address areas, rather than the MMU, which is page-based. The RISC-V processor is, well, our NOEL-V, I would say, RISC-V processor is a 7-stage dual issue. So being dual issue means that it could execute 2 instructions at a time, depending on the sequence of those instructions. So it's important that the compiler generates or layouts instructions in a sequence that is good for the processors. But compilers nowadays are very good at that. So that's very well. You get the benefit from this, even if you don't recompile your application with certain flags. So if you compare that with the Leon-V, it's also a dual issue pipeline in Leon-V. So you get approximately the same performance. But the big difference is, of course, the ISA and the functionality otherwise. It has a L1 cache. And you can see from the link there where you can find out more detailed information on the Leon-V. Next, please. So the different configurations, of course, you can set them to whatever configuration you like, but we have tried to minimize the number of configurations that we talk about. So we have tried to make a tiny configuration or a high performance configuration or a general purpose configuration to simplify both the testing for us, but also when we talk about this configuration, it's easier to find a use case for them and what we think makes sense. And we provide an FPU as well. And you can see from the configurations options here that it's also possible to change other parameters that doesn't affect the functionality as such, that doesn't compile change the compiler options. If you select a single issue, it will be compatible on the ISA level, but it would execute in a different speed, or yeah. But it's in order, so it wouldn't affect that way. Next, please. And I should have said that in all the configurations, it's possible to enable fault tolerance. We also have a debug module, which is compatible with RISC-V debug specification. And what's nice about that is that we can basically support third-party debuggers. So far, we haven't validated that, but it would not be, we believe it would not be a hard thing to adapt a debugger for our components or IP. It has a JTAG debug interface, which is compatible with RISC-V standard, but we also have the traditional other debugging links like Ethernet or SpaceWire as part of our existing offering for Leon. So that will be the same here as well. We reuse the ecosystems or IPs from GeoLib that Leon and NOEL-V is part of. So there's a debug support, which you can read about that. And to comply with standards, we also implement the interrupt controller of the RISC-V specification. And we believe it's important to be compatible in order for software ecosystem to well, it's easier to port code between different RISC-Vs and the porting efforts is basically lower. We do think that the NOEL-V can be used in the same bus architecture than that we use for new Leon 5, where we have developed a multi-bus, what we call striped AMBA bus, so that we can have several CPUs and several buses, so accesses can be done in parallel on those buses. For example, different addresses selects which a specific address selects a specific AMBA bus. So the interaction between the CPUs are positively affected, and we can also increase the bandwidth this way. But that means also we have the number of L2 cache instances matching the AMBA bus. And on the backside of the L2 cache, we would then have the same number of AMBA buses interfacing to our new DDR controller. And the DDR controller provides is a multi-port to take advantage of the bandwidth of the DDR. So we have seen that using this memory controller, we get the speed up of, I think, about 15 times than what's available in the GR740. So this is very interesting going forward. Okay, next please. The NOEL-V is available. It is open source and it's available in the GLL IP repository. You can follow that link to get there. So it's both in GPL, and if you want to design commercial designs, then there's also both a commercial and a FPGA and a full tolerance version of the license. There are pre-built bit streams which include some of those commercial licensed IPs in there, and those bit streams can be downloaded and programmed on your own boards. And GRMON evaluation version supports those bit streams, so you can download that and just connect it to the system, and you have a hardware debugger which is capable of the ordinary debugging and C++ debugging using GDB and downloading of applications and starting them, etc. Next, please. So the hypervisor extensions we've been recently working on, we've been compatible with the 0.6.1 specification, but there's a new specification also that we will plan to implement. It should be very similar. When we enable the hypervisor mode, then there's another mode. There's an additional mode. It introduces the virtualized supervisor mode and the virtual user mode, and then the completely new mode, which is called the hypervisor extended supervisor mode. So depending on the V-bit or the virtualization is enabled or not, you have a different number of modes. And the idea is that the guest OS would run, in principle, unmodified under the hypervisor. But when you enable the hypervisor, then there will be another extra step of memory address translation. So there's a couple of new CSR registers to control the different new features of these modes. And there are different registers in the different modes that is available. So the specification allows to delegate traps, for example, where you select which mode a trap should be passed on to. So the default, then the traps end up in the machine mode as usual, but then through the machine mode in registers, it can say that, oh, this specific trap should be handled by the hypervisor, and the hypervisor has a similar set of registers. So it can say that, well, that trap should actually be handled by a guest OS instead, or in the virtualized supervisor mode. And that way, that works. Next, please. And on a similar way, we have a hypervisor interrupts, where we can delegate and configure, the hypervisor can configure which interrupts goes to which mode. So it can delegate interrupts to, let's say, the guest OS directly without being involved, or it can handle itself and then use register interfaces to send manually interrupts to the guest OS, for example. There's a new APLEX standard, a new specification of a new interrupt controller, which we are evaluating to support, and I think that makes sense for us to go that way. Next, please. Yeah, I think we will skip this one, but basically the guest has physical addresses, but it's called guest physical, and then it's translated into physical. Next, please. And the area increases about 5% or so. Next, please. The PMP provides a more easier or more high-level protection of addresses than the MMU. That is also available. Next, please. Yeah, we can skip through this as well. Next, please. So basically, we have the PMP and also the page table walks going through the processor. We have done some simplifications, and where we store the page table walks and the PMP, which we have used at the same time in the TLB. So when we get a hit, then we don't have to look up both two TLB walks or page table walks and then also the PMP. That would be impossible to do in one cycle. So next, please. And this is the state machine within the processor. First, you see when we only had MMU support. And when the hypervisor is turned off, then the OS would typically use this approach. But when the hypervisor is turned on, then there's a lot of different new states that gets complicated in order to support all this. Next, please. So, of course, we need to test that, right? So we have different, yeah. I'm sorry, 1 minute?
Correct.
Yeah, okay. So what we've done here is that we sort of have shown how many, that we can boot Linux on the hypervisor enabled NOEL-V. Okay, and we've done that using Xvisor, which is open source, but we're also involved in other. And fault tolerance is done same way as Leon, but we have also improved it with hardware scrubber built into the L1 cache. We can go another slide, and then we have filed a patent for a new way of protecting in L1 cache. You can read about that if you want. Can take next slide. I think, yeah, this is what I wanted to present. So we've done a test chip on Leon 5 and NOEL-V on ST Microelectronics 28 nanometer technology, where we reached 1 gigahertz. So that on the Leon 5. So we have tested this at our premises now, and we're also doing a radiation test campaign on this. So this has been a collaboration between ST and ourselves, where ST uses this as a vehicle for testing their new technology, their cell library, and we do this to test our new processor IPs. So is time up now?
Yes.
Yeah, okay. Any question?
Unfortunately, no time for
no
questions. We
question.
do have
Okay.
several. We'll move those over to the Slack channel. Yep, and we can have
Thank
some
you very
of the
much.
discussion over there. Thank you so much, Daniel.
Thank you. Thank you.